Lecture 7a. 7a. Lead derivative. Spherical coordinates. Step 1. Write the curves generate the flow. First, the curve along time t. Flow of the capital X is the tangent vector. Okay? And the tangent vector a curve generated by the real t. T is a time, okay? Is a scalar. So the coordinates of the sphere are r, theta, and phi. Okay? The theta is the polar coordinate, and phi is the azimuthal coordinate. Theta is from the scale 0 to pi, and the phi of t is from 0 to 2 pi, the azimuthal. Where r now is constant, is sphere constraint. At point P, phi of 0, okay, is defined as x of I of 0, r, theta of 0, and phi of 0. At point Q, as we emphasized before, you see, point Q is phi of eta. Eta is a tiny increment, okay, which corresponds to the time tq. You see, at 0 is time, at p is time t, p is 0, as we did in the previous lectures. So these are Cartesian coordinates. Xi of eta is the function of eta is r. That's a point q is theta of eta and phi of eta. You see? So first, curve along parameter lambda. Okay, do you remember that here we have a parameter t and a parameter lambda, which leads to the tangent vector capital Y. You see, this is constructing Y. At point P, xi of lambda, you see r theta p of lambda and phi of theta p of lambda. Remember, theta is a polar coordinates, and phi is azimuthal coordinate from 0 to 2 pi. Theta is from 0 to pi, and phi is 0 or 2 pi. So at point Q, again, x is analogous, similarly, is xi of lambda, q r, theta q of lambda, and phi q of lambda. You see, this is a step 1. It's a setup, you see, setup of the spherical coordinates. Now, step 2, express the tangent vectors. Vector x along t, you see, parameterized by t. Then at point P and Q, you see the coordinates are r, theta, and phi, but r is constant. That's why it didn't appear, okay, on this relation here. The tangent vector x is not influenced by the radius r. You see, so this is a d theta of dt. This is a basis vector. See, partial of theta, partial phi are the basis vectors, okay, where dr dt is 0, as I said before, because r is a constant. The radius of the sphere is constant. Now, vector y along parameterized by lambda, okay, at point at P and Q. The same here, you see, that instead of t, the parameter is lambda. So the theta of the lambda, this is a basis vector, okay? This is parameterized along lambda. X is parameterized along t. So step 3, compute the push forward. You see, the push forward, okay, is take the push forward acts on vectors. Don't forget that. You see, so YQ is a vector. So the push forward of YQ which leads to the vector y tilde at p. You see? So, but this is a basis vector here, where the basis vector change because the manifold is curved. Attention now. You see, when you move from Q to P, okay, the basis vectors, okay, change. That's an important observation. So then, because the manifold is curved, if you have a flat manifold, then they will not change. So from here we compute the change in the basis vector. You see, this change in the basis vector will use the connection, okay, Christoffel symbols, see? As we did in many previous lectures. See, they computed the Christoffel symbols. Particularly on the sphere S square, the surface of the sphere, with coordinates theta and phi, the bases change when moving, okay, in this case in theta or phi direction, due to the curvature. You see that the curvature, the base vector change. So the change of the base vector along theta and phi. Now this along theta and phi, they are the directions. Okay, these directions, they are governed by the Christoffel symbols. See, as we did in many previous videos. Okay, so then you calculate the metric of the sphere. See, ds square is dr dot dr. See, so this is ds square is r square d theta square plus sine square of theta d phi square. The basis vector is partial of theta and partial of phi. You see, so this again, I will insist that there is no dr square here, since r is constant, the radius of the sphere. So that's the basis vectors, okay, on the surface of the sphere. Now, then we can calculate, say, the non-vanished Christoffel symbols for the particular case of the sphere, as again, I will say, this we did in many previous vectors, okay, that we derive all of this. So the gamma, the Christoffel symbol gamma phi of theta, it is symmetric on phi and theta. See, that's why they are equal to cotangent of theta. And this, the Christoffel symbols phi and theta is minus sine theta of cosine. See? Now, from here, we will transport the vector yq back to point P. That's a push forward. On this here, we'll see the next lecture 7b. You see? Just will continue this derivation here. You see? Again, don't forget that we are preparing to use the definition of the Lie derivative. Okay, don't forget that. You see? So we are preparing here for the particular case of the sphere.